particular, what we're going to do is we're going to create a node class, and then we're going to use that node class to be able to insert nodes into, or I said binary search tree, into a binary tree, not a binary search tree, right? Difference is a binary tree has no more than 2 nodes per root node, right, as children. Binary search tree, is the same idea except it is sorted data, okay? So we'll call this binary tree implement. And I will push this up to the repo, okay? So we'll go to binary tree implementation, and we're going to create a couple of base files. I am going to do a test for some pre-order stuff, but I'm not going to do it for in order and post order, because I want you to be able to build those tests out. And again, if you simply move a line of code here, everything changes in terms of how this gets read. Remember when I said read the data, then go left, go right? That's before. Go left, read the data, go right. That's in order. Go left, go right, read the data. That's post. Okay? So let's say make dir. We're going to make a node directory, okay, which is going to hold our node class. And then we'll touch an index.js. We'll let that actually be the BST implementation itself, so we have an entry point where we can add things to it. And then I'm just going to npm init-y, which will create my package.json file for me. And the whole idea behind that is that when I'm doing that, I need to be able to run something like jest, right, to run tests. Okay. Now that I have that, I should probably create a test directory, right, which is going to hold our tests for our application in it. So let's let that install. And again, the idea here is that we're going to create a node class, which is nothing more than a value and a placeholder for children, right? And then we're going to implement a BST, or I keep saying BST, a binary tree class, which will be to work with 3 methods: pre-order, in order, and post order. Those are your traversal methods. So what we are doing today, to be very explicit, we are creating a node class, we are creating a binary tree class, and we are creating 3 traversal or search methods. So when you start getting into next week, you're going to have challenges like find the maximum value in a binary tree. Well, you have 3 methods that you can use to be able to traverse the tree, right? And again, we're going to do this with recursion. You can do this without recursion. If you do this without recursion, you are not using the efficiency structure that has been put in place, basically, for this type of tree. That is taking way too long to install. That's okay. Let's do this. Just open a new one, just to open up VS Code real quick. Okay, so binary tree implementation. All right, so I'm going to go ahead and open up VS Code. And, oh no, you know what? We'll do that. Yay! I have this thing where I drag up to the top and it like expands. So I always want to drag, but it's easy to do that too. Okay, so we're going to start off with our node. Now let's talk about that for a second, right? I said start off with our node. We didn't put anything in our node directory, so we should probably create some sort of a node class. Now, let's talk about the structure of this. We did this like the first week in this class. Remember how I told you you could create multiple index layers in a file? In a directory structure when you're working with a node application? There is a common argument in the industry. When you have like an index.js that sits at your root, and you have a whole bunch of subdirectories, and then there's a bunch of index.js's in that. Those are indexes for this type of a thing, like a node. We could call this node.js, we could call this, BT node.js, it doesn't matter. I want you to see that this is a convention that is often used. I don't necessarily like it, but I want you to see it, okay? So that's a thing. That's different than index at the root. We're saying this is the entry point for any sort of a node class. Does that make sense?
Yeah.
Okay. So we're going to go into node, index.js, and all we're going to do is create a node. This is going to be really simple because we just need to make a basic node constructor. All right. So we'll do it like this. I'm going to do it a little bit differently than what you saw to show you a slight differential kind of showcase based on what we saw on the slides. There's a couple ways of building this. Okay. So we'll say class node. All right, and then we're going to do a constructor, which is going to have a value, okay? Let's set the initial values on this. This is ES6, so we'll say left is equal to null. Right? How many of y'all have seen this? No, it's not the first time actually. It's like the second or third time, but it's been a while. This is ES6. When we create, we saw it first week. When we create a new node, it's going to set its initial value as null for left and right. Does that make sense?
Yeah.
I mean, the left child is null, the right child is null. Value, we still need to pass it an initial value. Does that make sense? Okay, so we can say this dot value, right, this is a constructor, so this dot value is equal to value, this dot left is equal to left, right, and this dot right is equal to right. Now think about what I'm showing you up here, and this is actually really cool in relation to what we're going to be doing in React.js. We will do this in React.js all of the time, because React uses something called state, and state management needs to be set at some sort of initial state. Often we set our initial state to null or 0 or some sort of empty object. Okay? So we do a lot of this in React. All this is doing is saying, as soon as I create a new node, the value of that is null, the value of this is null, the value of this is whatever is passed in. Make sense? Okay? Say that again? Oh yeah, totally. If you want to say, you want to do it like this too? Same thing, right? It's just the same idea. All right. However, we're gonna work with this new pattern. What am I doing here? There we go. Do you understand what's happening there though? Everybody see this? So this is an initial value that is being set in a parameter. It's pretty cool, right? Yep. So now let's go below and we'll say module.exports.
Mr. Brian,
Yes.
can you show us the export and import? Instead of module export.
Not yet. Not yet. Nope.
Because this lint keep always saying exactly ES6, ES6.
That's one you're not going to convert to ES6 on yet. Let me explain that. In React, you're going to use import and export every single day of the week. It is super heavily, actually it's not even super heavily used, it is the standard in React. In Node.js, basic application development and more often in API development, the standard is still to use require. Does that make sense?
Yeah.
Why? I don't necessarily know, but it is the standard. And I want you to stick to the standard that's been in place for a long time for back-end development. That's the best way to think about this. Could we use import and export? Yes, we would say export node. That's all we would put, just so you know. And then on the other file, we'd say import this file. And it looks like this, just to show you. It's this simple. Export node. Missing something there.
Default something.
Yeah, I think you have to set default. You're right. There you go. Which is just the whole thing. That's the entire thing. And then on the other end, it would look like this. So, like, let's imagine we were importing it. It would be import, and then whatever the file is. So, you know, node index.js. That's the same thing as saying require. Does that make sense?
Yeah.
Same idea. Okay. But yes, you're right. So the important thing to think about here, and that's why I don't want to do it just yet either, is default is saying take the whole thing. You can also set up your objects when you're using like export to say export only these methods. When you import, you can actually bring in only certain methods of that, which we're going to do a bunch of in React. Cool? So module.exports is equal to node. So now we're going to jump back here, and we're going to go into our index file, and what we're going to do is create our BST class, no we're not. We're going to create a BT class. I give a lot of interviews with this, so that's why I do that. All right, so we're going to say use strict, okay, and we're going to say class. We'll call this, instead of BT, we'll just call it binary tree and make it real clear. All right. All right, and you're exactly right. We're missing a piece. What are we missing? Require a node. Let's talk about that in a minute. We don't necessarily have to require our node in this. We're going to create a node in our test, and then we're going to use this to pass it into this. Does that make sense? Okay. Now, we could bring in our node, and we could start to do things in here, but watch what's going to happen here in just a second. I think this will help.
If you want to test your class in this file, you will have to
You have to create it. Yep, you're exactly right. So we're going to say constructor, but I like the way you're thinking through this, right? We're talking about building separate things that we can create a node, start instantiating nodes as part of our binary tree class in our tests. Does that make sense? Okay. So we're going to say constructor, we need a root, right? Now, again, we could do something like this. This is just ES6, right? It is just saying let's set the initial value. So we'll say this dot root is equal to null, or well, we'll do root, right? There's no difference than what I just did, really. But at the end of the day, this is a new thing. Let's look at it. Cool? All right. And again, like I said, when we get into React, we will actually be using that for real purposes. Like there's a very important thing in terms of state management to say this initial value, which then gets updated progressively as you're building out new components and setting, or not building out new components, but setting up new state. Okay? Yes?
You must read it because when you now want to add a value, the value look like the node.
The value is the node.
You know, you must say it will be like that.
Nope, not yet. Not yet. I see what you're saying, right? You're saying we need to pull in the node here, right? Or we need to instantiate a new node in this. We are building standalone pieces so that in our test file we will instantiate a node and then we will pass that node in as a value for our binary tree. Does that make sense? I think it'll make more sense when you see the two pieces work together. We are building standalone modules. One is a node constructor, or I should say a node class. One is a binary class. They shouldn't be pulled in together necessarily like this. Does that make sense? Okay. So let's talk about what we're going to do. And I'm not worried about building tests for this beforehand because I'm more concerned about you understanding the logic of this. Okay. So we're going to do a pre-order. We're going to do an in order. And I'll let you do your own post order. Actually, you know what? I'll do this. It's easy. So I'll do post order just so you can see it. But I'll have you write your test for that one. Okay. All right. So here's the thing. Let's have a conversation around this first. Yeah, we should talk about this for just a second. TDD, like super important that you know that it's a thing. Super important that you're trying to push yourself in the direction of TDD if you can. What is the reality of the industry? The reality of the industry is that often you write some code and then you write your test, right? I want you to, and this happens in every single JavaScript class I teach, I want you to be much more focused on getting your applications wired together and built and understanding the concept of those things than focusing your time and effort on a test. Because you know a test is going to be a describe this module, right? It should do something. Here are the assertions for that. Does that make sense? Yeah. That's the structure of every single test. And at this point in time, while you may not be doing a bunch of TDD, you know what you know how to do? You know how to write a test because you know that those three components are what make a test. Make sense? If asked in an interview setting, do you do TDD? You're like, yep, sure. Right? Like that's how that works. And they will probably push you to do TDD depending on the level of company, right? So for example, if you were working at something like Expedia and you were working on a team that was building internal applications for Expedia, they're not going to worry about it that much. You're still going to be writing unit tests, but those things are going to be like, yeah, make sure you write a test for that. Not write your test first, and then we need to have your test pass, and then you need to, or sorry, fail, and then you need to go in and start plugging in your code. If you're working for something like Amazon, and in particular, you're building out like the AWS platform, not using it, right? Or if you're working at Expedia and you're building something for the client-facing layer of Expedia, then you're probably in a position where they're going to have checks and balances where you write your test should fail, they're going to look at your test before you even start writing your code. Does that make sense? Mm-hmm. It depends on where you work. I've had some pretty awesome conversations already with Ahmed and Mahmoud and myself. I've never been pushed in that direction to write tests first. It's just been, you need to write some unit tests for this. And often, you're in a position of time and money. Right? This is the reality. Software development companies are about generating revenue. And if you're in a startup ecosystem, they are not going to care. They're going to be like, we got to ship this thing as soon as possible. So what should be most important to you is that you're working towards TDD, but you're focused on the elements of getting your code to work. Shippable applications are the most, revenue-generating applications, meaning that if you have a week to build a thing and you spend 3 days writing tests and you don't get your thing done, then you're costing your company money. Does that make sense? So I just want to be super real about this. It depends on where you work. If you work at Amazon, there's going to be tons of time and effort invested into this. If you're in a startup, you may not ever write a test at all. Cool? Follow what I'm saying? Okay. All right. So, and these tests are pretty simple to work with anyway. All right. So let's talk about time and space. Okay? So with pre-order, we're going to do this recursively. We're going to say we want to go, so this is pre-order. Nope. We want to look at the data, then go left and right. So let's put a comment. Data, yep. Left, right. And when I say data, I just mean read the node. Then we say left, go left. All right, right means go right. That's about as clear as I can get with that. Okay. All right. So let's say let results equal an array. Okay. We good so far? Okay. So we're going to say let walk. Now, when we do an underscore convention like this, working with recursive structures, that is often meaning that this is a recursive call. So this is a convention. Follow what I'm saying here? When you see an underscore like this on a function name, it is often, not always, there's other reasons that you could use an underscore for the naming convention. For example, sometimes you have like, var, ID is such a great example. Well, no, it's not because we use ID elsewhere. But maybe we're going to say like var node, which is a node that we pass in. And later on, we want to say some node that we're referencing that is not the node that we passed in. That could be a difference in convention here. But when you write a recursive function, it is often in JavaScript represented with an underscore first. Okay? So to walk this tree or traverse this tree, right, we need to be able to walk it with a series of nodes, or look at a node, I should say. Okay? So this is a recursive function. When we talk about a recursive function, that means that we are going to be calling this function inside of the function. However, I'm going to jump out of this just to get you thinking about this. We also have to kick it off, right? So we'll say walk this dot root. Starts there, okay? This will make a little bit more sense as we start to drive through it. So the idea is that I can't just call this function in here recursively. I've got to kick the function off. So that's its initial firing of it. And then it's just going to go until it's done. Now, when I say until it's done, think about it like this. So say that again. It's. I used to say that, but yeah, it kind of is the best way to say this. It's not really a loop, right? Say it again. Spiral is kind of a way to think about it. Yeah, I mean, you can conceptualize it a bit in your head as a loop. Often loops can be built in kind of this recursion or recursive manner, but it has to be in relation to a recursive data structure. So for example, like when you loop over an array, that's not recursive. Does that make sense?
Yeah.
Okay. I just don't want you to get confused with that. So we'll say results dot push, okay? We're going to say node dot value. All right? Now check this out. Here is the recursion. We first say if there is a node dot left, okay, then we are going to walk node dot left. Okay, we're going to talk through this whole thing in a second. If node dot right, walk node dot right. Now, we need to return results at the end of this. Okay, so let's look at the piece of this that changes depending on if it's pre-order or if it is in order. Okay? So we said first we want to results.push. That means we are reading a node's value and we are adding the node's value to our results array. Okay, that's read the node, right? And this is pre-order, so what do we do first? Read the node. Follow?
Yeah.
Then, after we read the node, if that node has a left, we're going to walk it with node.left. That means node.left is a node. Remember how linked list was a node with a value that was a node? Or sorry, was a node with a value of the next that was a node? Does that make sense?
Yeah.
Same idea here. We're gonna print all this out so you can see some objects in a minute. Okay.
When you type underscore walk, what will this do?
Okay. Let's look at it like this. Let's visualize. Right? We got a tree. Okay. So we're gonna start with this one. Make sense? This is kicking it off. Walk this dot root. Now let's look at. Remember our node. Let's look at our node constructor here. All right. So here's our node constructor. We have a value, and we have a left, and we have a right. Left and right are nodes. We good so far?
Yeah.
Okay. Good. All right. So yes.
I'm sorry, continue.
Okay. Cool. I'm going to do it on here. Actually, this will make it easier to see. We have white space. Okay. So this is the cool stuff. It just gets tough to think about a little bit. And this is your first. We did some recursive stuff before. But this is like your first real recursive algorithm. All right. That's a really small chunk of code too, actually, when you look at it, right?
Yeah.
It's pretty elegant. So we'll say node has a value of 4, right? Which is a node object. There's a value, there's a left, and there's a right.
Yeah.
So we'll put a left on it. And we'll say the left is a value of 8, right? Again, this is not a binary search tree, it's just a binary tree. We'll say right has a value of 10. So to visualize this thing is an object, right? With a value of 4, and then a left, which is an object of that, right? And a right, which is an object of that, and those things have a value. And right now, those things have a left and a right of what?
Of null.
Null, right? Okay. I'm gonna redo that. Just make
Not all of this, what's the issue? How you call the function, you actually divide it inside. So you call the walk inside this walk function.
yes. So
This is
let's.
confusing.
It's crazy. All right. So let's say 8. 24. Again, it doesn't matter. This is binary tree, not binary search tree.
Yeah.
All right. Okay. So let's look at this whole function. When we call preorder,
Mhm.
all right, the first thing that preorder is going to do is going to look at this line. It's going to say results is an empty array. Then it is going to
So this one, yeah.
call walk. It is calling the function we just made here. This is just declaring the function. This is invoking it. All right. So it invokes it with this dot root. So it starts here.
Yeah.
Okay. And then it says results dot push node dot value. That's the first thing walk does. Follow?
Yeah.
So right now we have a results array. Our results gets 8. We good?
Yeah, good.
Okay. Then it says if node dot left, walk node dot left, which is a node. So then it goes here.
Yeah.
And walk says this dot root, or sorry, walk goes here because it's calling walk. It gets to this line.
So moving
push
forward.
the-
So we push the node dot value, which is 20. You follow what I'm saying here?
Yeah.
And then it says, now hold on a second. Then we move, we go if node dot right, walk node dot right. Is there a right? No. Okay. So then we recurse and we go right back to here, right? Which says results dot push node dot value. Actually, I got that. I'm gonna try to re-say that.
Can I rephrase that?
Yes, you can rephrase it.
Thank you. It's like creating, if we are going to the long way to solve this. We are going to creating a while loop for the left
That's exactly what this is.
and,
Yep.
and another loop for the right.
Yep.
So let's say like a pointer, current node will be current node if while current node dot left
Yes.
exists.
That's exactly what this
Yes,
is.
do push this node, then let's say
It's not
update
correct.
update no. Inside the while loop, you will update the dot left to be to move to the next left of the left object.
Yep, that's a lot.
Inside the, inside
Right.
the while
Yeah.
loop. Then after this while loop is finished, the whole function will move to another while loop to the right.
And so on and so forth. You're exactly
like,
right.
Similar to linked list, but moving into two nodes, not the next. Yeah, left and right.
So again, hold on. All right, let's go backwards. So, thank you. Right. While loop implementations are heavily used in this, we're doing a straight recursive solution.
Yeah.
Okay.
This is much
This-
cleaner. Than
It's much cleaner. It is also though. So yes, I agree with you. It's much cleaner. But I also want to let you know, and everybody else in here know, that recursion is one of those things that takes a while for your brain to capture. When your brain captures it, you're like, recursion is where it's at.
Yeah.
Okay. You cannot do recursive things though unless you're working with a recursive structure. Does that make sense? You have to have a recursive data structure to work with. So let's start again at the top. We'll say 10, 15, and 8. Okay? So the first thing that happens when we call preorder is this line is looked at. Results is just an empty array. The second thing that happens is that walk is called because it's now been registered. And it calls it, with this dot root. It says results dot push, no dot value. This dot root has a value. Okay? So it goes straight to it, which is 10. Then it says if no dot left, walk no dot left. That recalls this whole function with this dot root. And remember, every time we get to one of these things, we reference it as a root. Does that make sense? And we're doing, this is in particular pre-order, so the first thing it's going to do is it's going to read the node.
And then check if it has a left.
Check if it has a left, check if it has a right. It does not have a left, it does not have a right. So now what happens?
Go to the
We
next.
recurse,
Yeah.
right?
Yeah.
So we walk, right? And it goes boom, and it goes up the tree.
Go to the next if statement for the next.
You're
for
right.
The first value.
Is there no dot left? Yeah, but we've already visited that, right? So it goes here, and then it says, let's push this value. Is there a no dot left? No. Is there a no dot right? No. We cannot walk anymore. We return our results array. Does that make sense?
Yeah.
Okay. It's craziness,
Yeah.
right?
Mr. Brian?
This is super, super cool. So hold on a second. I think, was there a hand over here? No? Yes.
This is the truth. That's the point.
That's all it is. Like, basically the way to see this dot root, I want to make a bigger tree here, and I'll get to you in a second.
No, it's okay.
This, like, look at it like this. So, that's a bad color. We're gonna do like black or something. Okay, so check this out. So here's what I want to get you to think about, right? Let's imagine we're not gonna read all this data. We're just gonna look at this, right? This could be this, whatever. It doesn't matter. So we have a binary tree. Okay. This is the root node for this entire tree. And this whole tree has this as a subtree. Does that make sense? Right? So then when we visit no dot left, this is now considered the root of this subtree. Does that make sense? That's why we're saying walk this dot root. Follow? So root is basically the parent for each subtree. Follow?
Yeah.
Okay, cool. Go ahead, Ibrahim.
No, it's okay. After you finish, can I use the one for marker to
Yep, go for it.
simplify this?
Yeah. I'm gonna let you simplify it after we get through it, but yes.
Yeah, after this.
So I'm gonna build the whole thing.
Yeah, after
Cool. Okay. Yes.
Going back to my question, this before is true. It's not actual one. Does it have lift one to this district and this before?
Yes, it does. So root.
Did not initiate any nodes from class node.
Right, we haven't built that yet. We haven't made this all plugged together. We're thinking about if we got a bunch of nodes that have already been plugged in. Does that make sense? We haven't said add a node, add a node, add a node, add a node, add a node yet. So we haven't built a tree to even recurse. But if we had a tree, this would be the recursive algorithm that would look at it. Notice that nowhere in here have I said like new, add a new node, add a new node, add a new node, add a new node, add a new node. We're gonna do that when we get into our test file. Does that make sense? You follow what I'm saying there?
Yeah.
Okay. We're just talking about if we had a tree, this is what it would do. Cool? Okay. Yes. Go for it.
trying to refer, is it referring to factorial, like finding the factorial? Or is it like minus 10? Because we're looking on the right and stuff. Factorial is really
Yeah,
because
I mean, yes,
it keeps calling back until it's 1.
until it's 1. Yes, I would say yes. It is actually, it might even be factorial. Yes. We should look at that though. Yes. Okay. So hold on. Here's where I want to go with this. This is the important piece. Check this out. So this was pre-order. We had to think through what pre-order was doing, right? I'm going to take this chunk of code right here, okay, and I'm going to go into in order. This is why you should be able to build post order on your own, which I can build it for you because it's super simple.
Just switching.
All we're doing to make this different is we're grabbing this line of code. This is in order, right?
Command and down stuff.
Thank you, Ibrahim, but I can't see my mouse. Otherwise, I would be doing these things. All right, so okay, so hold on. Done. So when we get to the next one, which is post order, I'm not gonna do post order for you because you should be able to figure that out. If you have a hard time with post order, then you don't conceptualize what's happening. So I'm not even gonna put it there. Okay? Not gonna push it up. You definitely need to have that. But truly, this is where you actually get to copy paste when you're trying to implement here. Truly, if you build the one, then the only thing you do, if I take this line of code that says results out push, if I put that below, it is now post order. It is about the way that it reads the node. Does that make sense as to why we did that exercise together? Of saying like, read the data, go left, read the data, go left, read the data, go left, so on and so forth, right? It's because this is what is happening when we recurse the tree. That's exactly what this is doing. Okay?
Yeah.
We good? Okay. So let's talk about time and space of this. So for a binary tree, right, what do you think the time is for traversal on this? It's big O of n, right? Because we need to look at everything. Now space, we haven't really necessarily talked too much about space. Can someone try to explain to me what I mean by space efficiency? So time efficiency, the easiest way to think about that is one of these words. Search or traversal. That's time. How much time does it take to go find the thing? In the worst case. So let me stop there for a second. Big O notation is not about describing the best case scenario in an algorithm. It is the worst case scenario. What do I mean by space? Wait, hold on. Say that again. Variable in the memory. How much memory is being allocated for this, right? How much spatial memory is being allocated to work with this tree, right? You're very close on that, but I want to talk about it a little bit. We need to have a whole tree saved into memory, right? This one's a little bit different. And this can actually be described in another way too, but I like to describe this as O of H. What do you think that means? The height of the tree. Okay? I want you to do a little bit of discovery on O of H and what that means, right? But that means that in order to be able to reserve memory for this tree, in the worst case scenario, it is the height of the whole tree. That's how much memory is going to be allocated for the tree that we create and the tree that we traverse. Does that make sense? Follow a little bit? Okay. If this was my tree, which was level 0, right? That was my tree. In the worst case scenario, in order to save this tree into memory, it's an O of H, right? If I had this tree, which is a height of 2, right? In worst case scenario, it is an O of H, which is the height of the tree. So if you kind of think about H as an integer, you know, O of 0, O of 2, right? Does that make sense? We say O of n, it's because n number of items in something. So like when we're looking at a linear data structure like this, to traverse this, if we say O of n, in this case, you could say O of 4. Does that make sense? we don't describe it like that. We don't say O of the number of nodes or O of the number of items. We use N as a representational thing of as many numbers as there is. Some people actually use other variables on this. O of H is the height of the tree. Make sense? How much space needs to be reserved to be able to save this tree? Yep.
Could you please slow down?
Yeah. What do you need me to say?
Just to slow down your speed of the progress. Because most of us have an issue with big O
Yeah.
thing.
Okay.
Yeah.
Did you read about it?
Read about?
I know a little bit,
Yes.
not all.
Okay, so that one's on you.
So
so-
review things.
So time, space, search, memory allocation. We'll stop there for a second, okay? Big O. What is big O?
Roast.
Worst case of what?
Time space.
The data, search, amount of
What's
data.
the efficiency?
Time.
That's exactly what I was looking for. Big O is a measurement. I like the word measurement too. Of the efficiency, there's another thing to say here too. Efficiency of an algorithm. Ready for this next piece? Without running it. This is a descriptor. So measurement could also be used as describe. Describe the efficiency of an algorithm without running. Does that make sense? You're looking at it. Follow? We don't run the algorithm and say this has a flaw. We look at it and we determine based on the algorithmic structure and the data structure that we're using what the measurement of that is. That's what Big O is. So now there's two key pieces of Big O. There's time, and space. Someone tell me what time is.
Time to shoot.
It's searching through the algorithm, right? It's searching through it, right? So looking at each thing. Okay. So in a linear data structure, so let's do this. Okay. Here's one. Linear data structure, an array. Actually, I'm gonna do it like this. There's a couple things to talk about. So there is O of 1. Okay. There's O of the. There's more than these. Like this gets super crazy. Okay. All I'm worried about in your case right now are these. And this one we haven't gotten to yet necessarily, but we've lightly touched on today. Binary search trees are O of log n if you write them correctly, right? So the idea is you look at a data structure and you determine with this data structure if I need to find an item, that will be traversal. So first we're going to start with traverse. If I need to traverse something, right? If I don't really need to traverse it and I need to just put something at the end of it or put something at the beginning of it and don't have to go and look through it, here's one, an object. I.e., we're going to get into it later, a hash map. Object and hash map are the same thing. Okay, well, basically. The idea there is that if I add a property to an object, do I have to look through the object to add a property to an object? No. Right? Okay? You don't really traverse that. You're not looking to traverse an object. You're saying, put this property on an object. And in relation to an object, objects do not reserve, in JavaScript, objects do not reserve order. Let me rephrase that. They are not guaranteed to reserve order. So if you make an object and you say like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you're not guaranteed that you're going to get back those properties in that order. Does that make sense? Okay. O of n, linear. That means something like you got to look through this whole list of things to be able to find something. And in our case, an array is a linear data structure, a linked list, and so is a binary tree, or even just a tree in general. Binary search tree would be a bit different. Okay? This is for traversing it or searching it. Then we have O of log n. O of log n we like to call divide and conquer. And that means that we're able to cut it in half. Cut in half.
Like when you search tree.
Yep. Each time we search. That's cutting the time in half each time we're looking for an item. Cool? Say that again? Yep, big problem, and you just keep breaking it down into smaller chunks. Does that make sense? So it's like, you know, there's a, the best way for me to do this is make a tree. Sorry, I gotta sneeze. Thank you. Thank you. Okay, so let's do this real quick. I'm gonna help you understand this, and then we kind of took a roadblock here with Big O, right? Here's what's up with Big O. I think, if I remember correctly, and I was actually doing some work, if I remember correctly, Ahmed brought it up, but I think he may have just lightly touched on it. I brought it up the first week, and then he kind of lightly touched on it a little bit on Stacks and Queues week. So I'm okay talking about this some more, but it's important you read about it. It is also important that you don't go down the path of Wikipedia documents with this. Wikipedia is not going to teach you Big O. That's going to get super, super hard to read and intense. I want you to look at some basic, descriptor of Big O. Here is a great example of this. Ready? I'll show you one. Then we're going to jump back into this because we need to write a test for this. Okay? Is this helping you at all?
Yeah.
Okay. All right, so let's see. Let's go here. Check this out. It might take me just a second to find this, but there is a really great infographic that helps. Why won't this go over? Sorry, I can't get this to show up. Hold on. There we go. Okay, so we're gonna go back into it. There's a really great infographic for this. So Big O infographic. There's one that I really like. It's like super, super simple to look at. Hold on. Where is this thing? 1 second. I think it's worth it for us to take a second to look at this. Big O. Big O. Cheat sheet is one that might have it on it. Where's this thing at? Yeah, here we go. This is it. This is what I'm looking for right here. It's a version of it at least. This will show you kind of a version of what we're looking at the very least. That one's not loading up. Let's maybe this one's bigger. Here we go. Yep, this is great. All right, this is awesome. Okay, so yeah, this is super awesome. So we look at something like O of n squared. What does that mean? Before we even look at this, what is O of n squared? Yep, so it's O of n and then a nested O of n. A nested for loop is an O of n squared data structure. So, or not data structure, efficiency. That's one that you don't want to do, right? That's bad. So let's look at this. Here is the most efficient. O of 1, O of log n. Okay? O of n, linear. Okay? O of n log n. We're not going to worry about that right now. We'll talk about that very shortly. Okay? Say it again. 1 time and a half. That's right. Say it again. Sorry, I can barely hear you. Yes, root of n. You're right. And then this is O of n squared, and it's in the red, right? So what we're doing, we're trying to stay here as much as we can. Does that make sense? We want to live in this layer. Follow?
What's the last one?
These over here. O of n.
No, the next
No, see, these are things. Okay. Who cares? right? Who cares? Not efficient, right? Let's stop worrying about this right now. We care about, and I wouldn't even worry about yellow right now. We care about green land. Cool? Follow? So O of 1, O of n, O of log n. Those are the things we're working with right now. That means that when you build, let me be really clear with that. That means that when you come in and you try to solve a problem and you do it with anything that is like O of n squared, you should automatically be saying to yourself, no one is going to hire me for this. I got to think of a better way to do this. Does that make sense? So what is big O? What is big O? Yes?
Describe the efficiency of an algorithm without running.
Yep. You don't even really have to say without running it. I just want to kind of make sure you know that. But it's describe the efficiency of an algorithm, right? So when you go into an interview, it's not about just saying, like, this is where I think some of you all are going to get hung up. I think some of you all are going to say things like, I need to figure out the big O. It's not really about figuring out the big O. It's about looking at the problem you're trying to solve and coming up with the most efficient solution, given that data structures often have, efficient ways of searching and traversing them. Does that make sense? Okay. And then space is about how much memory is required to be able to save this thing. So check this out. So we'll say 0, 1, 2, whatever. This is, to traverse it, O of n. What is in the worst case, if I want to add an item to that, right, what is the spatial memory for this? Again, a lot. Who says O of n? Nobody's raising their hand. O of 1. We're not searching it, we're attaching to it. Yes, it's one item. It's one thing. Okay? Okay. Okay, so hold on. All right, everybody, hold on. Okay. Big O notation. What are you going to do to try to figure out big O? Read about it. Read about it, right? Don't get hung up on the term big O. No one cares that you know what big O means. What they care about is that you know mostly, and it's not even really about space. Space is not the most important piece. It is mostly about being able to traverse it. It's about time. Does that make sense? We all follow? Okay, good. I hope that helps. Did that help a little bit? Okay, awesome. So here, we got to write a test and we're gonna be done. So we need to say module exports is equal to, and again, I didn't do post order. You should definitely be able to do post order binary tree. The difference between these pieces of code here, right, and this one here is literally the placement of results.push. If we said console.log node.value, you could do that too, right? And that would log the value of the node. Does that make sense? We're just trying to read each one and collectively get it. Okay? All right, so let's jump back. We're going to go into our test file, and we're going to talk about plugging this up. And I think this is where people were like, hey, why aren't we bringing in our node class? Why aren't we bringing in our node class? Well, let's find out why. And actually, I don't think I put a test file in there. So we're going to say cd into, we need to make dir, dunder, we'll call it tests or test. That literally doesn't matter. Boom, jump in that. I would say test actually is better for this because we only have a test. Right? We're going to touch binary tree test dot test.js. There we go. Okay, and let's open it up. Okay, so let's do some cool stuff with this. So we'll say use strict. Now, first off, we did not in any way, shape, and form make a binary tree. We just made methods. Did we? So that's where people were getting a little confused too. They're like, well, where's this tree thing at? We didn't make a tree yet. We made a class for a binary tree. We made a class for a node. But when we talk about walking our tree, we're going to walk a tree that is there. Does that make sense? I can't walk a tree that's not there. Otherwise, it's just going to return null,
No.
right?
So we need to
Yep. So we should say const binary tree is equal to require. Now, why is this capitalized?
yeah, because it's a class.
Yep. Index.js. And then we should say const node is equal to require. That one is in node, and then we said index. So one of the things you can do when you have like an index.js like this is one of the things you can actually do in Node. You can omit that entirely because it knows that index is the entry point. But again, I don't like that. You can do it, I don't necessarily like it. Cool? That's part of the reason why people will do that, because they'll have huge directory structures where the directory tells you the actual name of the thing. Okay? That's a Node thing. So let's say describe binary tree. Right? And we're going to create a function that describes our binary tree. So let's start with let tree equal null. We're going to start with an empty tree. Okay? And all we're going to do is before every single test we write, so we'll say, actually we should do before all. Yep. And we'll talk, what's the difference between before all and before each? Does anybody know?
I know before each it will implement the inside this function before every x.
Mm-hmm. It's before every it. Before all is before every single expect statement. Does that make sense?
So before all inside the it.
There is an expect.
Yeah,
that's correct.
Yeah, maybe we'll be like firing this function to all.
Yeah, so if we had to expect, it would do another one, expect, another one, expect, another one. Now, I'd say before each in this case is probably going to be fine, because really all we're going to be doing is just looking at a single expect, which is my pre-order thing expected to be equal to the thing that I made it? Okay. However, you can use these methods as you choose. There's a before. There's a before by itself. There's a before each. There's a before all. There's an after each. There's an after. There's an after all. Right? So this is where everybody's like, well, which one do we use? I don't know. Right? Whichever one you want to use. Is everybody kind of seeing too with these things that are available to us in Jest, how it is your decision, not mine? Does that make sense? That's why every time we get into like talking about code review and I push up a piece of demo code and I want these things to be different from your labs, it's specifically because I want you to discover your own way of thinking through this. Right? I use before all in this. I'm going to give you a hint. The way that we're going to write our tests, before each would be completely fine as well. Because really all we're going to be doing is having one expect statement in each test, and before each would do the exact same thing. It would run before every it block. Make sense?
Yeah.
Okay. So we'll say before all, we're going to run a function. All right. And all we're going to do is just make some new nodes. So we'll say let 1 equal node. Sorry, we got to say new node. New node. And we'll pass it 1, right? Sorry. And then I'm just going to copy that a few times. Actually, we'll do a couple. So we'll say 2 equal new node. 2. Let 3 equal new node. 3. Let 4. I would copy paste this right now if I could see my mouse. 4. And then one more. Let 5 equal new node 5. And actually, that's not a big enough tree. I want to get the tree large enough so that when we console log it, you can kind of see what's happening. So let's do 8. Let 7. I hate typing. Node equals 7. And then let 8 equal new node. We're going to be done right at lunchtime, by the way. New node 8. Okay, so we have this, right? So now what we're going to do is we are going to set a couple things. All right, watch this. 1.left is equal to what? What do you think? 2, right? Then we could say 1.right is equal to 3. Now look, think about this. Think about our implementation of this. 1 is a node, right, which has a value of 1. Okay? And then we're like, all right, let's set its left, which is a new node, which has a value of 2. And And then we're going to add a new node, right, to the right, which has a value of 3. Now that we're here, let's go a little bit further with that, and we could say 3 dot left. Or sorry, actually, it doesn't even matter. We have to make let's make it random. Let's not make it its normal tree. So we'll say 3 dot left is equal to yeah, we could do 7, but let's at least try to keep it in some order, right? 3 dot right is equal to 5, and then let's do 2 dot left is equal to 6. 2 dot right is equal to 7. And then we'll do, actually let's do 6 dot right is equal to, let's do 7 dot left and right. And then we'll add the, yeah, so 7 dot left is equal to 8. And then that's all we have, right? Yeah. Did we use 7? Yes. 2 dot right is 7, 6 dot right is 7. So I have to have a 6. So we'll say 6 dot right is equal to 7. Or sorry. So this is where it gets kind of hard to implement. So 2 dot right, let's just do a 2 dot left. And then, which is 6, so then we could say 6 dot left is equal to 7. And then we'll add one more, because we have 7, right? And we have an 8. So then we can say 7 dot, I don't know, right, right, is equal to 8. Kind of follow here? We're like building a tree, okay? Now check this out. Now that we've done all this, look up at the top here, let tree equal null. Now we're going to say tree is equal to new binary tree, right? And we're just going to pass it 1 because that is the root node. And the root node has all of these nodes added. So when you are in an interview, are you going to be building this crazy thing? No. What you're going to do is you're going to write a function that will accept a binary tree as its input and will do some sort of operation. Does that make sense? Okay? Well, there's nothing left, that's it. Right? So let's do pre-order test. And I'm only going to do pre-order test because your post-order test should be really similar to it. Okay? You're just going to call pre-order or post-order. All right, so let's do it, pre-order. And I like this convention. This is a thing that I do like. I do like you doing that when you're working with method names. I think it makes it clear that you're working with a method. Okay, so we'll say let expected equal, we got to think through this. So this is going to be pre-order. So it's going to go, oh man. You know what? The easiest, we're going to make this easier without making this tree crazy to think through. Bam. All right, let's make this easier. My goal here is to try to not add complexity. This is a small tree, but at least it'll do what we want. So hold on. 2, 3. So 1 dot left is 2, 1 dot right is 3, 3 dot left is 4, and 3 dot right is 5.
We don't have 3 and 5. We need to.
Oh, good call. Yeah, just keep 4 and 5. Okay, so let's think about, see, pre-order is going to be interesting to think about the way it orders it, right? So actually, let's do this. Just so that we know what the heck is happening, so that we don't have to think through the ordering of this and like try to do it in our brain, let's make this really easy. Let's say console, because hopefully it'll work. Console.log, we're going to say tree.preorder. That's going to print out a results array. Does that make sense? That we can then get, and then we can just test against it to see if it works, right? Normally what you would not do is this, but I'm not going to try to think through the traversal of this. Does that make sense? Right? So run it. And we'll get an array. So we'll say node. Oh, sorry, we're doing a test. That wouldn't work, right? So let's jump in here. Everyone that's talking, you should probably not be talking. I'm going to say that again. Everybody that's talking, you should probably not be talking. All right, so we're going to go into package JSON. We're going to say test. We're going to do npm run test. We're going to do jest dash for both is all I care about. Right? All right, so let's jump back in here. Let's say npm run test. Make my tree. Great. So 1, 2, 3, 4, 5, actually. Yeah. Because we put them in a specific order. So that's awesome. All right. Well, that works. Hold on. Oh my gosh. So let's open code. You know, I love this screen. Just so you all know, I'm like really feeling the screen, but the small mouse thing and being able to like see tiny, tiny dots where I have to like move my mouse to click, that's a bit frustrating. Like right now, I'm only using the like background color. I'm gonna mess around with that this afternoon. I'm gonna spend some time with it. Okay, so because the way we did this, that's right. That is absolutely right. Pre-order processing. 1 dot left is 2, 1 dot right is 3, 3 dot left is 4, and 3 dot right is 5. That would actually pre-order process exactly in that order. So we know that we're looking for 1, 2, 3, 4, 5, right? And we'll say let expected. This is why testing this is a little interesting. Say it again. We don't need to loop through it. We could, I mean, we could, sure. But then that would be defeating the purpose of working with a binary tree. Does that make sense? Like, you see what I'm saying? So what I did here was I cheated to get the result of this so that I didn't have to like think through exactly what that was doing. And then we'll just say expect pre-order. Now our test did not pass earlier. I want to talk about that for a second. To equal, and we'll do expected. Right? And pre-order needs to be called, so let's do it like this. We'll say let pre-order equal tree.preorder. Boom. All right, there we go. That's what's up. Okay. This is what we're expecting this to do, which is the order of it. I console logged it to see if it was. And then we're saying, let's go ahead and call preorder, pass it in here. It's just a cleaner version of saying this. And then let's run this test. Now notice, I want to show you something. This is considered a false positive. Notice when I do this, and I run this test, this is a false positive. Because this said you passed this test, and it says check, pre-order, right? No, I didn't, because I didn't even write an assertion. So note my key terms here, right? I said assertion. This is the assertion. This is the test. Does that make sense? So boom, save it. Now let's see if it actually does. Which it should, because we just logged it. Right? Passed. Good. So the interesting thing about this is that when you're dealing with things like testing of these, you really have to have a clear understanding of how this is formatted. Here's what I used to make students do in an interview, and I stopped doing it because it would waste so much time. I would say, just go ahead. You don't need to build a BS or a binary tree class. You don't need to, show me how that works. Like, what I need you to do is I need you to create a function that accepts a binary tree as its input. Let's come up with a sample binary tree. And then what ends up happening is students are like, all right. And then you start here and you're like, okay, a node, right, which has thing, right, which we call it root, which has a value, which has a node, and you just, it goes like this. And then everybody gets confused and you start missing brackets and it becomes too long, right? Does that make sense? So that is a bit of a challenge when you're working with things like a binary tree, but the idea here is that really you should be able to read this in the order that it's supposed to be read in, right? And as long as you can do that, I'm not necessarily concerned as much about your tests, because your tests are often going to be you running the code to see if it builds the thing, and then you just copy and paste that to check it, which is not really a test. So what you could do is you could write some better tests, and I think some better tests for this would not necessarily be testing that your binary tree works necessarily, because we ran it to see if it worked. You could do something like this. You could say expect pre-order dot length, right? Dot to be I don't know, 1, 2, 3, 4, 5. 5. Does that make sense? Like things like that. You could do expect, pre-order, or type of, pre-order, dot to be array. I think it's like to be a.
No, array is array.
Oh yeah, you have to do to be array dot is array.
Because there is not a no type of.
Yeah, you're right.
Or you can use objects.
Yes, so if you use an object, it'd be fine too, right? So these are, I would say these are actually better tests. Sorry, not that one. These are better tests than this one here because really we ran it to see that that would give us back data of that. Does that make sense? Right? Okay, now let me also tell you something really quick. When we're going through and we're doing these things like to be and to equal, here's where my brain gets confused, and I'll tell you why. I started working with something called Mocha and Chai. These are still very heavily implemented in the industry. Mocha is a test runner. Okay, that means it runs tests. Chai is an assertion library, which means it's these things here. Jest was built after Mocha and Chai put together. There's Jasmine. Jasmine does this too, right? Very interesting names, right?
Yeah,
Mocha,
no,
Chai,
that
Jasmine. There are a few other ones, and they all follow the same idea. It's these things. All of them actually are expects. Almost every single one of them is expect. In fact, guess what? You could do this on your own without any of these frameworks. Node has an assertion library called assert. You could just say require assert, and it's their assertion library. It's just not as verbose and not as fully featured as this, but that's built into Node.js. Cool? All right? Okay, I will take one question, and then we have 2 minutes. What's up?
Just
Perfect
curious,
time.
How long will in order input will take to create this string? Because I noticed that in order to take only 5 or milliseconds back into the terminal.
You mean like the amount of time?
Yeah.
I have no idea.
Comparing with all time.
Yeah, I don't want you to think of, so I think I see what you're saying. You're actually looking at the actual time. Yeah, that's not what you're necessarily looking at here. We're not trying to compare one algorithm being 3.2 milliseconds versus 3.6 milliseconds. We're trying to say in the worst case scenario, this is going to take more time than doing something else. That's the bigger thing with Big O. It's like this.
Response time.
Say it again.
Response time.
It's response time, but we're not, again, there's a difference in how much actual time it takes. We don't care about that when we're talking about Big O. We're looking at it as a descriptor of how much or how efficient it should be given the data structure that we're working with. So for example, instead of saying one took 3.2 and one took 3.6, what you should be doing is saying O of 1, right? O of log n, O of n. Does that make sense? Yeah, kind of follow what I'm saying there? And then cool. Does that help? You're say it again?
You can use this time to see the difference between these algorithms.
Yes.
You can use it declare a variable with the time before execute the code.
Yep.
And you declare another variable after the code and subtraction between each other to see the difference between the
That's actually a good, so that actually is pretty interesting to talk about, right? What you're saying is like if we implemented it with like O of log n versus O of n, we could hold one and see how long it took and the other one take. That's actually interesting, right? Because in that case, almost in every case, if it's the same algorithm, this is going to take more time than this is going to take. Does that make sense? But this, what we're working with here right now is right here. Does that make sense?
Yeah, because
You're stuck on like 4.6 milliseconds, like that.
because this is what's big O about.
No, it's not.
For time of
It's about looking at an algorithm and being able to tell you what is more efficient given the data structure and the type of data structure you chose. If I'm working with an O of n structure and I have both, if if I run this same code again, like exactly same code again, maybe I have something running my computer in the background, right? Maybe I have another thing happening over here, and that's going to cause it to be like a 0.2 milliseconds off. Does that make sense? That doesn't matter to us. That's not what we're looking at. But what does matter, to your point, is that if we had a for loop, right, versus, I don't know, a recursive structure, you know, this one's generally going to be faster than that one. Does that make sense?
Yeah, for his point, I can use console design.
Yeah, but if it's
It's the same time.
it's no, it's not, because it depends on what's running on my computer. It depends on your computer. That's why we're talking about describing the efficiency of an algorithm versus running the algorithm and saying this is 5 milliseconds, this is 5.2 milliseconds. So to answer your question, like, look, let's run this again. Well, here, I'll answer it directly. This took 1.71 milliseconds. Or sorry, it took 1.212 milliseconds. Let me, you know, open another app. Like if I have music playing in the background, right, that's going to take a different amount of time. So it was 1. What did I do? Oh, I'm not worried about this test right now. Hold on. You're getting granular with this. Like you're trying to actually look at the actual physical time of this. That's not what Big O is about. It is about if we use this. So look, I run the test. Okay, 1.22 is longer than it was last time. If I run it again, it might be 1.065. Does that make sense?
There's 4 milliseconds.
You're going in the wrong direction. I'm trying to help you with this, but you're definitely.
This is the time when you are running in your device.
Yes.
But the method gets reordered. Where is the check? Next to 4 milliseconds.
After
For
snapshot.
each test.
Okay. This is the exact same test as the one I just ran. They are identical tests
New device.
on my computer. On your device, you might have 4 things running. I might have a bunch of programs running. And every time I run it, my computer is doing operations in the background. It's processing information. We are talking about describing the efficiency of an algorithm based on a data structure, not based on actually how fast it is in my computer. Does that make sense?
Yeah, but just to finish this discussion, just did you notice that line when you check that you just pass
Yes.
the pre-order for 30 seconds? Next to reorder, when you describe that it's
It took 4 milliseconds.
yeah, that's time. With for each test the same time, 4 minutes. 4 minutes.
No, that's 4 milliseconds, and it's giving you a break. That's not the exact time. It's probably 4.0137 the first time, and maybe 4.0175 the next time. Jest is giving you the rounded version of that number. Does that make sense? Okay. So are we clear on, like, it doesn't matter actually how long it takes your computer? Okay, that's what I want to make sure everybody understands. Big O is not about how long is this running on my computer. It is about the way it's structured and the way it should run. O of n is going to take more time than O of log n in the worst case scenario. Does that make sense? Okay, cool.
Sorry with that.
No, you're okay. I get it. But I want to be super clear, like in terms of, listen, when you're optimizing algorithms, that's when you start doing stuff like this. And you're going to be using that, like optimizing of an algorithm is going to take place on a supercomputer, generally speaking, and people are going to just do really small little things to try to just quickly make it better and better and better and better. Our goal is to say, when I look at this thing, this is faster than that thing.
Yeah.
That's the way to do this.
Because big of one at your computer the same as Alan Turing computer.
Yes, like
It's the same.
for example, like yes, you're exactly